it's 5:35, so let's get started. Today we're going to finish with chapter 5, and thanks to the excellent memory of at least one of my students, I'm going to start in the correct place, and I really should have made a note for myself, but I forgot. So we're going to finish with chapter 5 today. After we go through the rest of the slides in chapter 5, we're just going to work example problems until people get sick of it and decide that they want to go home and walk home in the rain. So that's the plan for today. Before we begin, are there any questions?
Is it really going to rain?
Yes.
Well, supposedly.
The forecasts say yes, but I am not, in charge of rainage, so I don't actually know.
The weather people tell us.
Well, yeah, I'm not a weather people. Although one of my master's students some years ago was a weather people. A guy named Dave Schaefer, of whom I'm sure none of you has ever heard, because he left here many years ago and moved to Utah. But that's it. Anyway, any other questions? Questions I might actually have a chance of answering. Not like what kind of weather is it going to be. My mother used to, not my mother, my daughter used to flip her pen like that. She learned how in debate class. Okay, so I've been told that we were on this example 5.4 from the book, on an elevator accelerating upwards. And so we've got an elevator suspended by a cable, and it speeds up as it moves upward from the ground floor. We're supposed to identify the forces and draw a three-body diagram of the elevator. So let's see if we can do that. Here is the elevator. And presumably the elevator is supported by the cable, because we're told that it's suspended by a cable. And remember, cables, like ropes, can only pull, not push. So here's the cable pulling upwards, right? So we're going to call that force T for the tension in the cable. In addition, of course, always whenever we have a problem that's on or near the surface of a large gravitational body like the Earth, we have the gravity force, which I'm cleverly going to call F sub g. All right. Now, what about the relative size of these two arrows? Well, we know that it's speeding up as it's moving upwards. If it's speeding up, then the acceleration must be in the same direction as the velocity. The velocity, we're told, is upwards. So there must be an acceleration upwards. That means that the net force must be upwards. That means that the T force must be bigger than the gravity force. Okay? So this arrow must be bigger than that arrow. Let's see what the book says. Well, the book says exactly what we said. Here's the elevator. We can see that it has gravity force and tension force on it. We see that the tension force is bigger than the gravity force because the thing is accelerating upwards. So there's a net force upwards. Okay, here's an example quick check problem. We've got a ball hanging from the ceiling by a string, and it's pulled back and released. Which is the correct three-body diagram just after release? Okay, so let's see if we can do this problem. Right, here are the pictures that we're given of the possible alternatives. Okay. We've released it, so our fingers no longer exert a force on it. Okay? Remember, things don't have any memory of what used to be touching them. You only put forces for things that are actually happening right now. We know that there must be a gravity force on the ball because we're on or near the surface of the Earth, and that must be directly downwards. So E and D are total garbage. Why are E and T total garbage? Because for some reason they have gravity pulling sideways. Gravity doesn't do that. Gravity only pulls straight down towards the center of the Earth. Gravity has no idea that you're suspending the ball from the string. It's just going to pull towards the center of the Earth no matter what. So D and E are garbage. We can throw those out. We have to have an arrow directly downwards for the gravity force. So that leaves us with A, B, or C. What other forces are on the ball? Well, once we put in the long-range force of gravity, then we only look for touch forces. What is touching the ball after we've let go? The string, and only the string. So there should be only two forces on the ball, the gravity force and the touch force from the string. That's it. What direction should be the force from the string? Well, it's a tension force, so it's got to be along the line of the string, and it's got to be pulling, because strings only pull, not push. They can't push, they're floppy. So there are two forces. This is garbage, right? Because there has to be another force. This is the only correct alternative. We've got the gravity force and we've got the pull force of the string. What's wrong with C?
There's another.
They've put in a third force. There is no force pushing the thing this way. There is no force pushing the thing this way. That will be the direction of the acceleration of the ball, but you don't put that in as a force. It's not a force. You put in the long-range force of gravity, you put in one force for every touch, then you stop. So this is the correct diagram. Yay! And look, they've labeled the forces correctly now. Isn't that smart of them? Okay, here we have a skier being pulled up a hill. Here's the motion map. We've got the velocity arrows at 3 distinct times. We've got no acceleration arrow. Why do we have no acceleration arrow? Because we're told that the rope is pulling the skier up at constant speed. Something is moving in a straight line at constant speed, so therefore the velocity is constant. If the velocity is constant, then the acceleration is 0. So the motion map is just this with a notation a equals 0. Now, if a equals 0, what do you have to have? By Newton's second law, you'd better have that the net force is 0. That's also Newton's first law. Ah! All right, what are all the forces on the skier? They have to sum to 0, so let's make sure they sum to 0. First, we put in the gravity force. Always put in the gravity force for objects that are on or near the surface of a large gravitational body like the Earth. Notice it's pointing directly downwards, which is good, because that's the direction the Earth's gravity does, in fact, pull. So we put in the gravity force. Now, we put in one force for every touch. 2 if it's a surface, possibly 2 if it's a surface. Clearly, there's a tension force. That's a pull force, because strings only pull, not push. And look, there's the tension force right there. It's along the direction of the string, and it's pulling, so that's correct. Now, there's only one other thing that the skier is touching. That's the ground. Because that's a surface, you can have 2 forces. Surfaces always exert a normal force, that is pushing outwards in a perpendicular direction from their surface, preventing you from sharing the space. And so there's that normal force right there. But they can also exert a kinetic frictional force or a static frictional force. That's the force that's along the surface. Notice that there are two directions, normal force and frictional force. One is perpendicular to the surface, one is along the surface. We went through this last time, so I'm sure you remember. Then we stop. And we make sure that the sum of those forces must equal 0. Why must it equal 0? Because the acceleration is 0. Let's not trip and fall and break silly neck. Okay. That's it for the chapter 5 slides. So we're going to stop there on the slides, and now we're just going to do example problems. Okay, who has a question on the slides or on chapter 5 or anything else? Anything?
I'm good.
Everybody's good. I knew that. I knew that. Okay, well let's turn to the examples and the exercises and problems in the back. Okay, so let's do at least one prob from each section. Right? In section 5.3, identifying forces, I assign number 4 to you. So let's do 5. Sure, why not? So number 5 says, so chapter 5 probs. So number 5 says, An arrow has just been shot from a bow and is now traveling horizontally. Air resistance is not negligible. Identify the forces on the arrow. Remember that we always neglect air resistance unless we're told not to. Okay, so here's the arrow. There's its little featherage. There's its arrowheadage. I just like to draw arrows.
All right.
It's kind of weighty, but you know.
Little
Tell me all the forces on the arrow.
gravity.
All right, let's draw the arrow just as a particle model, a dot. All right, sure, let's put in gravity because there's always gravity on any object on or near the surface of a large gravitational body. What other forces are on there? Well, we're told, I mean, it's only in the air, okay? So the only thing it's touching is the air. But we are told not to neglect air resistance. Since it's traveling horizontally, this is the direction of its velocity here, air resistance must be opposite to the direction of velocity. So I'm going to put that in this way. And I'm going to call that F sub air. It's the friction of the air. It's got to be opposite to the direction of the velocity because it's a frictional force. Right. Everybody okay? That's it. We put in the long-range force of gravity, this force of gravity, and we put in the only thing, a force from the only thing that it was touching, which was the air. So now we're done. Everybody okay?
Yes.
Great. All right, let's go to section 4. I assigned number 9. Let's do number 10. Why not? Remember, I will always do any problem that you ask me to do. If it was an assigned problem, I'll just set it up for you, but I'm happy to do anything you want. Okay, let's do number 10. For an object starting from rest and accelerating with constant acceleration, distance traveled is proportional to the square of the time. How do we know that? Well, we know that because if it's traveling with constant acceleration, then it obeys the first 3 equations on our formula sheet, and we know that one of those equations is x equals x naught plus b naught t plus 1/2 a t squared. So you can see from this formula that the distance traveled, which is x minus x naught, is proportional to the square of the time. Right there. Okay, if an object travels 2.0 furlongs, whatever that is, in the first 2 seconds, how far will it travel in the first 4 seconds? Well, if it travels 2 furlongs in the first 2 seconds, in the first 4 seconds, how do we know how it does? Well, it goes like the square of the time. So if it's twice as long of a time, it's 4 times the distance. So 4 times 2 furlongs is, I get 8 furlongs.
8
I don't know what a furlong is. Does anybody know? Well, we can look it up. All right. So that was easy. Okay. Let's see. Okay, from the next section, section 5.5, Newton's second law, I assigned you number 15. Let's, oh dear, they're all graphs, which means I'm going to do drawing on the board. Oh dear. Let's do something I can actually draw. How about number 12? I can draw a straight line, at least sort of. So 12 has this figure. This is acceleration in meters per second squared, and this is force in newtons. And this is 10 and 5. Right, and since I put the units here, I don't need to label these 2 numbers since I put the units here. All right, and what we want to know is what's this number and what's this number. What force values go in the blanks on the horizontal scale? We want to know what those two amounts are. Okay. So we're told that this is an acceleration versus force graph for a 200-gram object. So the mass is 0.200 kilograms. And we know that the net force, F net, presumably this is F net, is equal to the mass times the acceleration. So we're just asked to find F net if we know what the acceleration is. But that's easy, because we know the mass. Right? So this number right here should be 0.200 kilograms times 5 meters per second squared. So what's that? 5 times 2 is, yes, 1 Newton. What about this one here? Now this number here should be 0.200 kilograms times 10 meters per second squared.
That'd be 2 Newtons.
I get 2, yes. 2 Newtons. Well done. Everybody okay? All right. That was actually pretty easy. It was just the hard part was drawing the graph. Okay, didn't assign you anything from sections 5.6 or 5.7, but then there are a bunch of problems. So let's do some problems. So I think I assigned you number 33. So let's do number 34. So 34 says a constant force is applied to an object, causing the object to accelerate at 10 meters per second squared. So F equals constant, and A equals 10 meters per second squared. What will the acceleration be if A? F goes to F over 2. The force is halved. Well, how do we know that? Well, we know that the mass is not going to change, and we know that the F net is the mass times the acceleration. That's Newton's second law that we're trying to learn in this chapter. Okay? So if the force goes to half the force, then that means that the acceleration will go to half the acceleration. So 10 meters per second squared will become 5 meters per second squared. Everybody okay?
Mm-hmm.
Fairly easy. What about B? The object's mass is doubled. M goes to 2m. Well, again, we know that F net equals ma.
I think it's actually the object's mass is half.
Oh, I'm sorry, did I misread that?
Yeah, I think you.
Oh, you're right. You're right.
You're 33 now.
I'm doing 33. Sorry. Yeah, the object's mass is halved. Thank you so much. M over 2. Now what happens? Well, the acceleration should be doubled, shouldn't it? So the acceleration should be 20 meters per second squared. Let's look at C. C says the force and the object's mass are both halved. So F goes to F over 2, and M goes to M over 2. Well, if this is halved and this is halved, then the acceleration is constant. So A goes to A. 10 meters per second squared. Nothing happens to A. Let's see. The force is halved and the object's mass is doubled. So D. F goes to F over 2 and M goes to 2M. Did I read that right this time?
Yeah.
Yeah, amazing. Okay, so the force is halved and the mass is doubled. So the acceleration should be 1/4. All right, what's 1/4 of 10? How about 10/4?
Perfect.
Everybody okay?
Yes.
All right, great. So that was 34. Okay, let's do, all right, the next one I assigned you is number 43, where we, for these problems, you're supposed to draw a motion diagram, a force density diagram, and a free body diagram. Okay, so the one I assigned you was a rocket being launched straight up, so let's see if we can find another. How about this one, number 46? you've slammed on the brakes and your car is skidding to a stop while going down a 20-degree hill.
All right.
All right, so here's the hill. That's not too bad. All right, here's your car.
What a nice one.
Yeah, it's a box. Well, what can I say? I can't draw a car. All right, and it's skidding to a stop while going down, right? So what are all the forces on, oh, sorry. First we're doing a motion map, okay? So I'm gonna draw, and this is the picture of the situation. Here's gonna be the motion map. So here's the object here, the car, right? And at first it's going fairly fastly, but then it's slowing down. So I'm making the dots closer and closer together for my motion map, okay? Because the car's slowing down. So now I connect the dots with arrows. All right, I can't draw, but that's okay. All right, and I label them. V1, V2, V3, V4. So there's my velocity arrows. Now I'm going to switch color and draw in my acceleration arrows. Okay? What color is purple okay for acceleration? Sure.
Yes.
What direction should my acceleration arrows be?
The opposite way.
Absolutely. Remember, when you're speeding up, your acceleration has to be in the same direction as your velocity. When you're slowing down, it's got to be opposite of the direction of your velocity. When you're turning, it's got to be perpendicular. Sometimes two things are going on at once. So you could be slowing down and turning, or you could be speeding up and turning. But in this case, we're just going in a straight line. But we're slowing down. So just as you just said, the acceleration should be opposite direction. You can see that because here's the final minus the initial. It's going to be an arrow pointing that way. So I'm going to call that A12. I'm going to call this one A23, and I'm going to call this one A34. Whatever. You can call them whatever you like. That's just what I chose to call them. Oh, got my arrow over A34. Actually, let me just do 2 acceleration arrows since I've only got 4 things going on here. But you can see what I'm doing here. I just didn't want to make the picture so busy that you couldn't make out what I was doing. It's not a very good drawing anyway. Okay. All right. So there's my motion map. Right? Now they want a free body diagram. Right? So I'm going to do that right on here. Okay? So tell me all the forces on the car.
Gravity.
Gravity! We've got to put in gravity because we're on or near the surface of a large gravitational body like the Earth. And the direction of gravity has got to be straight down towards the center of the Earth because that's the direction gravity pulls. Gravity doesn't know you're on an incline. It doesn't care. All right. So we've put in gravity. That's our only long-range force. Now, I put in at least 1 force for every touch. If it's a surface, I might put in 2 forces. And in fact, there is friction going on here because I'm skidding down the hill. So I'm going to have 2 forces from my touching the ground here. One is going to be my normal force, which is perpendicular to surface, and one is going to be along the surface that's supposed to be directly along the surface. I just can't draw. And that's going to be my kinetic friction. Why is that kinetic friction and not static friction? Because the 2 surfaces are scraping over each other. That's the difference between kinetic and static. Kinetic means scrape. Static means the 2 surfaces don't move with respect to each other. They can move together, okay? That's static friction still. But if they're scraping over each other, that's kinetic friction. Okay, so it's only touching the ground. So those are the only forces that are going on here. But I'm still not done with my free body diagram. Why not? I didn't put in axes. You should never forget your axes. What direction would you like me to choose my axes? Well, here's a general rule for what direction to choose your axes. Always choose one axis in the direction of the acceleration. You don't have to do that, okay? You know, this is not a rule from Mount Sinai or physics. Physics doesn't really care. If you do the problem right, you get the right answer no matter where you put your axes. But it makes the problem easier if you put one axis in the direction of the acceleration and then the other axis perpendicular to that direction. So I can see which direction the car is accelerating. It's accelerating backwards. So I'm going to put my x direction in that direction, and I'm going to put my y direction perpendicular to that. So that's the direction I want to do it. That way, my net force is going to be a positive number in the x direction. Okay, now I'm done with 46. Should we do another one?
Yes.
Sure. How about 48? So sorry, this was 46. All right, let's do 48. 48 says you jump down from a platform, your feet are touching the ground, and your knees are flexing as you stop. So I am not going to try to draw the figure with legs and everything like that. I'm just going to draw the figure as a box, because I can't draw. I'm sure most of you can draw, but I can't. All right. What's the motion map?
Gravity going down.
Oh, okay. You're doing the free body diagram, which is fine. Okay, that is just fine. Yeah, unfortunately, I can't really draw very much here. You are in contact with the ground, and your knees are flexing as you stop. In other words, what's happening here is that you're just squishing yourself, really. Okay, I can't really draw a motion map here. Okay, because although the picture is like this, what would the motion map look like? Well, that would be a dot, a single point. Remember our particle model at your belly button. At your center of mass, which is approximately your belly button. You know why your center of mass is approximately your belly button? It's actually lower for women than it is for men usually. Well, I mean, when you were in the womb, that was in fact your center of mass, and you could rotate freely around your mother's umbilical cord. Once you actually were out of the womb and were growing up, your center of mass changed. Okay. And women tend to have lower centers of gravity than men. Men tend to have more superstructure, but whatever. Anyway, all right. So if we use our particle model and we put a dot for the position of the center of mass of the object, it's actually going to go downwards. So I'm you know what? I'm going to draw it bigger. So. Like that. You're coming to a stop. Your center of gravity is actually getting closer and closer to the ground, but it never actually hits the ground unless you're actually flattened out on prone on the ground, which is probably not good. All right. So what direction is your acceleration arrow? Yeah.
Opposite.
Yeah, it's got to be opposite to your velocity since you're slowing down. So I'm going to draw it like this. Like that. Okay? All right. So sorry about my terrible motion map. Now I'm going to draw the free body diagram. Okay? What are all the forces on the person jumping down? Gravity. Gotta put in gravity. There it is right there. And now the person is touching one and only one object. Touching the ground. Yeah. And the acceleration is upwards. So I'm going to put the normal force from the ground bigger than the gravity force. Does everybody see why I put that bigger?
Yes.
Right. What's the last thing I need for this free body diagram to be complete?
Your X.
I need my axes. Actually, I don't need an x-axis. I mean, I appreciate that you put in, but since everything is going on in the up and down direction, I actually don't need an x-axis. I can get away with only one axis. What direction do I want to put my axis? I want to put it upwards because my acceleration is upwards. So I'm going to put that in right there. I'm going to call that y. All right. Let's do another one of these. We're getting very close to the end of this chapter here.
Yeah.
Whatever. All right. How about number 51? Okay, we've got a spring-loaded gun shooting a plastic ball. Trigger has just been pulled, and the ball is starting to move down the barrel. The barrel is horizontal. All right. I'm going to draw this. I can't draw. Everybody okay? So here's the spring. Here's the ball. That is a ball.
That's great.
All right, I think the ball is still in contact with the spring because the ball has started to move down the barrel, but I'm going to say that the spring is not totally uncoiled. So the spring is still in touch with the ball. Although we're not given that detail, so I'm making that up as I go along. But here's my physical picture. What's my motion map? Well, here's my ball, and my motion map is going to say that it's going to go faster and faster and faster as the spring pushes it. Okay? It's going to make the ball accelerate. So here's my motion map, and you can see that in my terrible drawing here, my velocity arrows are getting longer and longer. So I'm going to label those V1, V2, V3. And what direction should my acceleration arrows be?
The same way.
The same way, because I'm speeding up and I'm moving in a straight line. So I'm going to say that this is A12, and this is A23. And then I'm just going to draw 2. Okay, I've got my motion map. Now I want my free body diagram. Tell me what forces are on the ball.
Gravity.
I'm putting in gravity. And it's absolutely. There it is. There are at least 2 other forces, okay? Because I can see that it's in contact with the barrel of the gun. I know this is a terrible drawing, but I mean, you know that it's in contact with the barrel of the gun, right? And you have to have something from the contact of the barrel, because why? Because otherwise you'd have a net force in the downward direction, and you know the thing doesn't disappear through the barrel. It doesn't go right through the barrel, right? So I'm going to put that there's a normal force, and I'm trying to draw that the normal force is the same size as the gravity force. So that the net force in the up and down direction is actually 0. Does that make sense?
Yeah.
All right, great. But there's also a sideways force. There's a sideways force because it's touching this spring. And we know the force from the spring has to be that direction, because why? Because it actually accelerates in that direction. So I'm going to put F sub spring. Now, there's possibly one more force. Tell me what that possible other force is. Yeah, friction from the barrel. But you know what? I'm going to neglect that. Because why? Because the friction from the barrel is going to be really small because the ball is rolling.
Yeah.
This is why we invented wheels. Because once things roll, we actually lose very little energy to the rollage. There is a small amount of static friction, and we'll talk more about that later when we talk about rolling. There is a small amount of static friction because otherwise it would slide, not roll. But this, to a very good approximation, is enough. All right, what have I still left out from my free body diagram?
Your axis.
My axes. What direction do I want my axes? I absolutely want one in the horizontal direction because that's the direction of my acceleration. And then I'm going to use another one that's perpendicular to that. So I'm putting in my axes like this, X and Y. And I can put them in up here. and not down here, because here it's easier to see them and it doesn't get messed up with my force diagram. And remember that arrows are arrows, and you can translate them perpendicular as long as you maintain their same direction. You can put them anywhere you like and have the same arrows. Okay, so that's 51. Let's do 52. Are you okay with this?
Yeah.
All right, 52 says, a person on a bridge throws a rock straight down toward the water. The rock has just been released. Okay, so here's the bridge. Here's the person. Here's the rock. I know it's a terrible drawing. All right, motion map for the rock. Well, it starts out with a non-zero velocity. Because why? Because we're throwing the rock down. We're not just dropping it, we're throwing it. So it starts out with a non-zero velocity like that. But then it speeds up. Because why?
Spring.
No, there's no spring.
Gravity.
Gravity! Gravity! Gravity's pulling on it. All right, I'm trying to draw, but the arrows are getting longer. I know I can't draw. All right, so I'm going to label those V1, V2, V3, V4. All right, what direction is my acceleration? It's got to be down because the rock is speeding up. So therefore, the acceleration has to be in the same direction as the velocity. So I'm going to write that as A1, oops, A2, A3. However, I'm trying to draw that all three of those acceleration arrows are exactly the same size. Because why? Because I actually know what that acceleration is. Once the rock has left the person's hand, it's only gravity that's going to be acting on it. We haven't done the free body diagram yet, but I already know that that's what I'm going to draw. And I know what the acceleration due to gravity is. That's little g, 9.8 meters per second squared. So these should all be the same length, all these acceleration arrows. All right, now let's do a free body diagram. Here's the rock. It has just left the person's hand. What are the forces on it?
Gravity.
Gravity. F, G. Anything else? Nope.
No, because it just left his
It just left his hand. Hand isn't touching it anymore. Hand isn't touching it anymore. The rock doesn't remember. Rocks are not good at remembering stuff. Okay? Yeah. It is touching the air, but remember our rule. Don't put in air resistance unless you're told to. In most cases, it's negligible. And in particular, in this case, it is. So we're done. Okay? With all forces. There's one more thing I need to put in, and that is axes. I'm going to put my y-axis that way. Because that's the direction of my acceleration. And I always like to put the one axis in the direction of the acceleration. Okay. Okay. How about number 55?
Okay.
Oh, sorry, you got a question?
No, I was like, okay, let's go with it.
Okay. 55. A heavy box is in the back of a truck. The truck is accelerating to the right. Draw a motion diagram and blah, 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 blah. All right. So here's the truck. This is a top-down. No. Here's the box. Box. Here's the truck. I can't draw. Here's the person driving the truck. I don't know. Some darn thing. All right, we're interested in the heavy box, and the truck is accelerating to the right. This is this requires a 3D picture, and I just can't draw a 3D picture. So you know what? I'm going to draw that's the all right. Here's a top-down view of the truck bed. Here's the box. So truck bed. Top down. So this is the direction of gravity. And that's to the right, okay? Now if the truck, okay, so first off, we need a motion map, right? What's gonna happen to the box? I'm drawing the box as a dot. What's the box gonna do? Well, the box is on top of the truck bed, and as the truck goes to the right, the box is going to be dragged with the truck to the extent that the friction between the box and the truck bed is large. If the truck bed is covered with an oil slick or something, then the box will not be accelerating to the right. The only way it makes it accelerate to the right is the friction between the truck bed and the. So we need to make some assumptions here. The truck goes this way. What happens to the box? Make some assumptions. I'll draw two pictures if you like. Let's first do, there's lots of friction, okay? If there's lots of friction, then the box accelerates with the truck bed, right? Which means if the velocity is this way, this is, let me just label this velocity. So this is velocity of truck, and this is the direction to the right. So we're going to say that the acceleration is going to be that way. So I'm going to say that I'm just making this up as I go along. This is the large friction assumption. But you know, it still has acceleration this way. So I'm going to make it go just like this. How's that? I'm trying to draw a curved trajectory with velocity arrows tangent to the curve at every point. I'm going to call those V1, V2, V3. What's the direction of the acceleration? Well, the direction of the acceleration is going to be towards the center of the circle. So that's going to be this way. That's the large friction assumption. What's the free body diagram that goes with that assumption? Well, all right, I'm going to have to draw two pictures for the free body diagram because I can't draw in 3D. So I'm going to do a sideways picture for the up and down forces, and then I'm going to do a top-down picture for the sideways force, right? So the friction pushes it in the rightwards direction. This is, again, the top-down picture here. This is going to be the direction of the friction. This is going to be the direction of gravity. And this is going to be the direction of the normal force. All right, this is the large friction assumption, right? But there could be a very small or even zero friction assumption, which means that this thing goes away. Which means that according to the truck is going to go like this. But according to the truck, the box is going to go like that. But what actually the box does is it just keeps on going with its constant velocity in this direction. Or this direction, depending on which picture you're looking at. I'm sorry, I can't draw. Everybody okay?
Yep.
Yeah, great. Oh, well, you know, this pretty much is the end of the chapter. Yeah, you want me to do another couple? Pick some if you want. Otherwise, we're sort of done with the chapter.
It's a simple chapter. That's the problem.
It's a very simple chapter. Yeah.
I like the examples. I think
Okay.
I'm good with it.
You know, we have until 7:45.
Yes.
Or we could just go home early. Up to you.
I'm good with it.
All right. All right.